Do you think these are the only number that exist? Let's see. Okay, we will again draw a number line, and on the number line, you will take a number, say 0 and 1 and 2. Okay, let's say this is a square whose side is 1 unit. All right, looks like a square. Now, that means this length, let's name this point as O, this point as O, this is A, let's name it here, A and B. Can we find the diagonal of this square, this length? We can easily find using Pythagoras theorem. If this is 1, this is 1, we can say OB is equal to square root of 1 square plus 1 square. 1 plus 1, that is square root of 2. That means OB is equal to square root of 2. Now, if we draw a circle taking center as O and OB as radius, so that circle would look like this, you know, it will be around this point. That circle would look like somewhat like this, but we are interested in this point over here. The circle will cut the number line at this point. Let's say that point as, name that point as P. That means our length of the radius of the circle should be equal. This length would be same as this length. Yes, our OB would be same as OP. OB is equal to OP is equal to square root 2. Hey, what did we observe? We observed there is another point P on the number line, which is equal to square root 2. That means square root 2 is also lying on the number line. Can we write square root 2 in the form of P by Q? We had defined the rational numbers in the form of P by Q, where P and Q are integer and Q is not 0. See, under root 2 can be written as square root 2 by 1. Now see, this is not in the P by Q form where both P, your P is not an integer, right? So it is not in P by Q form. That means there is another family of numbers that lives on this number line, which are called irrational numbers. The numbers like square root 2, square root 3, and the square root of all non-perfect square number like square root 5. Because if we say square root 4, this is 2, so this is a rational number. But we are talking square root 5, square root 7. Likewise, we can say a lot of number are there, square root 11, square root 13. So all these number also lie on the number line. We can easily show, actually we will show it by construction in the upcoming lesson, how we can represent square root 2, square root 3, square root 5 on the number line. But right now we can see like these are also the number which will lie on the number line. And these numbers are called irrational numbers. All right, so let's define irrational numbers. A number is called irrational if it cannot be written in the form of P by Q, where P and Q are integers, and of course Q is not 0. So we define rational numbers, those numbers which can be written in the P by Q form, and irrational numbers are those numbers which cannot be written. So we can give example of irrational numbers. So these are very nice example. Another example, very famous example is pi. You know what is pi? Pi is circumference divided by diameter. We will talk about pi little later. Now let's give some other example of irrational number. Okay, consider a number like 0.01 001 0001 4 times 0 1. See how beautiful this pattern is, and this continues like this only. You can see the number is non-terminating, but it is non-repeating also. The pattern is not repeating, it's getting renewed every time, you know. And another example we can give is like 0.12, 122, 1 triple two, okay, 1 3 time 2, 1 4 time 2, right? And this pattern also, if continues like this infinitely, that is also an irrational numbers. Likewise, we can give many irrational numbers between any two rational numbers, right? Now see, if I give another example, 0.120, 1230, right? Isn't it fun? 12340, 12345 all right, like that it continues. So it's also, see, make sure that you write this dot dot dot, that means this number is continuing forever like this. So these are example of irrational numbers.